of example, next page, you have this interior frame. So basically they wants to know how much UDL load coming on to each portal frame. By the way, this is portal frame. So this is portal frame. If I draw it up, that's question is to ask you if the wind is coming, how much UDL load it will going to apply due to the wind load on the roof and on the frame. So that's the questions that they are asking. Um, the roof has a pitch of 7.5. So if you take a pitch, like if I redraw this one here, so this is 7.5 degree. Okay, so with the horizontal line. The frame are 6 meters center to center or 600 millimeter center, and height to the eaves is 500 millimeters. So let me explain you 600 center to center distance. So the frame that you can see, the distance from frame to frame is 600 millimeters. So 6000 millimeters, sorry, another one 6000 millimeters, and that is continuous. So that's the informations. That's center to center distance of the frame 6 meters. Height of the eaves. So generally, if you typical structures, you have eaves. So you can think of, let's say this is the one. So this is eave of the building. So this height of the eave is 5000 millimeter or 5 meters given here. The door for the buildings are as shown. So there is a door number 1, door number 2, door number 3, door number 4, and there are 5 doors given on this structure. The door for the buildings are shown, and there is a fixed roof vent with 130 millimeter airway for the halfway to the length of the ridge. So by the way, this is ridge. RIDGE. This is ridge. Like if you have top part of this roof, it is a ridge. Then it says that the doors for the buildings are shown and fixed roof vent with 130 millimeters. So they say that at the halfway through, so whatever 24, so about 12 meter on each either one side of it, it has this opening. It has just the roof vent, so it is 130 millimeter of opening, that's on the roof, and that is on the halfway through the roof. Consider two cases where all door openings except the roof vent, so roof vent is closed, so we need to consider that all doors are open. So this is open, this is open, this is open, this is open, and this one open, and close, and then you close it off, and the critical openings are open. So I will explain you what is critical opening next week, but keep in mind that they want to have two cases, that you keep all the door open and what would be the force onto this frame, and if you keep all the door closes, what would be the force on this frame. So that's the typical. Let me ask you questions. What do you think, if I keep all the door open, does the pressure or the effect of wind force is higher or smaller? So let's say wind is coming, right, and I keep all the doors open. What would be that effect? Should be the worst case, or it is good to keep the door open when the wind's coming? When the winds comes at your home, strong winds comes at the home, we generally don't look that there is a pressure here, external pressures, and if you keep the door open, then you are increasing the internal pressure as well, and if you combine external pressure and internal pressures, it would be serious effect on your structure. So it depends on windward wall and which doors are opening. You are partially correct, but generally if you have a closed structure, like completely closed, and if you hit the wind, it will just have a external pressure only. Internal pressure very minimum, maybe some leakage is there, so you have internal pressures. If you combine them, if your door closed, you will have only external pressure, which is severe. But if you keep the door open, then you have external pressure, and then you have internal pressures as well. So if you combine both of them, it would have a serious effect. So that's, but it depends where which doors you are opening and so on, and which side the direction is covering. So you write, but generally speaking, closed door would be the better. We will check. We will have both case, so we will see what mathematics will tell us which case would be the worst one. Okay, so that's good. Yeah. By the way, any questions there in the questions that you don't know, because it is good that you understand all the vocabulary given in the questions. I can stop here and you can ask me the questions if you have any questions there. Let me know. Any vocabulary or any wording that I skipped through or you did not. Vent, a fixed roof vent or 130 millimeter airway for the half length of the ridge, right? So what is the length of the ridge? Length of the ridge is 24 millimeter. 24. Okay. Now it says that it is halfway to the length. It could be either side of the halfway to length. So let's say halfway through. Let's put it here. Let's say 12 millimeter here. Sorry, 12 meters here. And you have these air vent opening or fixed vents, which is 130 millimeters for 12 meters. So I hope it's clear. So today's we will not going to finish whole examples. We will just going to calculate the design wind speed. Okay, because there are two kinds of parts where we're going to calculate the velocity, design wind speed, and then we calculate the pressure and then force. So this will comes next week. This week we just going to stop at if you remember that we have only one equations that typically is we going to go through it. This is an equations site wind speed, that V site beta is cardinal direction, 8 different cardinal directions, V air MD site exposure parameters multiplier, sorry, and they are put it in a bracket because there are 3 site exposure multipliers. Therefore, it's written M. Design wind speed, that's V design theta that we need to calculate. So this is 2 page that we just need to just half a page that we need to focus today. So I'm going to write this equation first in the close 2.2 site wind speed. Let me turn off my camera. And if you have standards, if you have a different standards than me, probably it will not be huge difference. I printed this one in 2006 months ago. Probably if you feel that okay there are some difference and something, just speak and I will try to accommodate or we will discuss what is the difference. These standards every now and then they are just putting some minor changes. So it's not an issue. Whatever the standards you have, you follow that. So V site wind is equal to VR MD, MZ cat, MS, and MT, right? It has 8 different values. This one has 8. 8 different values. Right, it has 8 different values. Why is 8? Because if you think of north, south, east, west, northeast, southeast, southwest, and northwest. So that is 8 different directions. Therefore, we have 8 different value. Now this is called site wind speed. There may be 8 different site wind speed that we're going to talk through. Now first one we are going to work through VR. What is VR? What is the definition of VR? Definition of VR is given here. Regional gut wind speed in meter per second for annual probability of accidents of 1 over R given in the section. So you say that AEP, annual probability of accidents, is 1 over R and is given in the section number 3. By the way, this is a closed number. This equation is given in closed number 2.2. So we need to calculate VR. For this VR, if you go to the section number 3, section number 3 here, section number 3, we have some details given here. I think yesterday I discussed, but I will revise you again here as well. Probably it's not oriented correctly. So that's good now. So now this is the regional wind speed. But before we going into the regional wind speed, they have a written 1, 5, 10, 20, 25, 50, and 100, and so on. Now what is that? What is that R? R is the average recurrence interval. Let me explain you what is average recurrence interval. I think I explained you this one um, uh, yesterday, but let me put R. R is called average recurrence interval. That is the representation of R. What is average recurrence interval? If I want to put in the physical contents, that okay, let's say you have 100 years of data. Bureau of Meteorology, let's say measuring the velocity 100 for 100 years. Okay, they constantly measure over the all over the Australia, and they measures, let's say they have 100 years of data so far. So say that okay, any particular wind, let's say they right now whatever the suburb you are sitting, for particular your home, there may be in your suburb or near suburb there is a one anemometer sitting right now which is measuring your velocity. They are collecting the data. So any particular given time, let's say over the 100 year, they measure let's say they measure 41 meter per second in after 10 years. In 30 years, let's say again they said 41. Again, let's say 50 years they record 31 meter 41. So let's say they measure 41 over the 5 years. They found that for this 41 meter per second, it comes 5 times in 100 years. So recurrence interval is 20. Right? So I hope you understand that 20 years. It means that what is the physical meaning of this one? That 41 meter per second comes once in every 20 years. So if you have 20 years, your home will be experiencing, it is average, by the way, it is average. It may not hit, but it's average. So it says that whatever the recurrence interval R represent that year saying that that event or that particular event is going to occur once in that particular in that many years. So you will have 41 meter per second in once in every 20 years. So that is the representation of R. So let me go back and so explain you here. So V R equal to 1. Let me zoom. Okay, that is better. So R equal to 1, V equal to R equal to 1. So 1 year. So 30 meter per second it comes every year for region 1 to 7. 5 years. 32 meter per second comes once in every 5 years. 34 meter per second comes once in every 10 years and continue. Right? So I hope you understand the physical meaning of this data presented here. Right? So that's the story about R. I think there is a story about, I think I have written some return periods and so on. So return period, how often this speed comes along, as I mentioned. So annual probability occurrence is it is a probability that event that will we talk about happens in any particular years one. So this is just annual probability of accidents. I think I have notes here that for examples you have a return period, let's say 500 years. Okay, so your wind speed comes once in every 500 years. So annual probability of accidents is 1 over 500 times by 100. So you have 0.2% chance occurs this year. So probably every year it will have a very low probability that you get it here. Now how are you going to get this data? Probably you need to go back to these standards. Here I'm repeating myself again. So if you go back to the standard, which is 1170.0, and if you go through these tables here in table 3.1 where it's written annual probability of accidents, it has different importance levels, right? Importance levels 1, 2, 3, 4 and 5. It's depending how crowded your structures, like something in a rural area or in Alice Spring or in desert, probably there is one storage industrial buildings, and not many people are going there, and just for storage purpose or some materials that we don't use it, they store it for many years. Then let's say they have importance level 1, right? If the structures comes down, the loss of human life is very minimum. So that is important levels 1. The medium consequences of the human life, for examples, our houses and all, probably they falls in number 2. The high loss of human life and economy, for example, hospital, fire station, and where you have a problem of the let's say airport and all, they have importance levels of 3 and 4, because it will have a social and economical impact on the country. So then you want to protect those structures. Higher the important levels, you need to make it more stronger structures. Like if you want to build very high importance, the cost will increase as this goes high. Once you select your importance levels from here based on your classification, you can come here. You can come in table number 3 to have annual probability of accidents. In table number 3, we will have design working life. Okay, probably that's your client or someone. They will tell you that okay, the design build. Let's say you are designing for 25 years. They said okay, my structure should have a serviceable life of 25 years. So they said okay, 25 years, importance levels 2 or importance level 3. Based on that, you will have 1/250. So this is a return period, by the way. If you have 50 years, importance levels 2, we have 500. Generally, we go for 50 years. That okay, if we have structures, we generally make it 50 years. For specific iconic structures, we make it 100 years, but normally we will go for 50 years important levels with return period 1/500. So that's how you decide the return period or annual probability of accidents 1/500. This is 1/r equal to 500. So I hope it makes sense. So that's the story about this annual probability of accidents. Let's say for our case we have let's say for our case we have important importance level 2 that is coming from table 3.1 of AS1170.2. I can show it you again here from these tables. Medium considers importance level, normal structures and structures not falling into the other levels. So that's I pick. Let's say we will design for 50 years. Let's say we design for 50 years. So if you turn the page over, design working life for 50 years. So if you turn the page over, this 50 years important levels. So annual probability of accidents is 1/500. So from table number 3.3 of AS1170.0, we have annual probability of accidents is equal to 1/r equal to 1/500. Means that this recurrence in average recurrence interval, average recurrence interval equal to r equal to 500 years. Right, so we can say that VR equal to V500 equal to. Now we can go back. Let's turn this one here. We need to find the region to find the. We need to find this region. To find the region, we need to find the regions. You can turn the page over. There is a map for Australia, and by the way, on the next page you have it for New Zealand. New Zealand also use these standards, so they have it for New Zealand. Now here, what was the city in the questions? Canberra. Okay, so if I zoom in, and if you have a standard, can you help me out to find the Canberra and tell me which regions the Canberra is sitting. A3. So you have a Canberra here, and in that Canberra you have a region A3, right? So I can repeat again. This region A is divided into further A1 to A7, and there is a back on the New Zealand, and the map is divided into 5 regions A, B, C, D, and W. But here we have Canberra, so we have A3, and that is given on figure 3.1.A wind region. Okay, so region A3, everyone agree? So we will take it. We will take region A3. Region A3 because we have city given Canberra, and that is in figure number 3.1A, right? And that region A3 Canberra, I can show it to you here, that you have given Canberra here. All right, so so for that case, region A3, we can go back in the table. That is region A3, region A1 to A7. So there is a region A3, and so we will go on these first columns, and we found V500. We have 45 meter per second. What does it mean? So region in A3, there is a chance of 45 meter per second coming once in every 5 years. Okay, so that is the meaning, physical meaning of that one. V100 500 will be 45 meter per second. This one coming from table 3.1, right? So first one is done, which is VR. Okay, now we will go for MD. So MD, what does it calls? MD. Now if you turn the page over, you will have MD here on clause 2.2, and the definition of MD is wind direction multipliers, and for 8 cardinal direction, which is represented by beta and is given in section number 3. So it's wind direction multiplier, and it's in the 8 different cardinal directions. So let's go back and find it out. Section 3. If you go to the clause 3.3, wind direction multiplier MD, you have a region A to W. So we are in region A3. So we have region A3, and for this A3, we have 8 different directions. Now in these examples, the question does not say, like unlike in the lectures, it says that wind is coming from west side only. Now in this example, it does not say that wind is coming from wind direction. Wind is coming from any directions. We can't say that, okay, wind is coming only, I'm going to design my structures only wind coming from north side or south side. The wind can be come from any side with any intensity. The intensity is not intensity we don't know, right? The standard will tell you how much intensity, but it will comes in 8 different directions. That standard says that. Now in these tables that you can see here, particularly this table, I will like to have a physical look. In these subjects, I want to have a physical feelings, what those each value and what the physical meaning in the real world. Now in these tables is telling me that MD is 1, and MD is between 0.8 to 1. Sorry, MD is varied from 0.8 to 0.1. If it is less than 1, meaning that wind coming from that particular direction is less intensive, it's less. If it is 1, meaning that you are multiplying 1 here. You are multiplying 1, you are not reducing your speed. But if you multiply 0.9, let's say, then you are reducing by 10% of your wind speed. So that's what it's meaning. The 1 meaning that is the strongest. and less than 1 meaning that direction is not strongest. So if you look at these tables for those regions, you can see this is only region A3, it has 0.9, 0.95 for region A4. But typically in Australia, you will see that the wind coming from the west side is the strongest. Okay, so this is not me, Bureau of Meteorology is saying. So wind does not blow equally from every direction. As I mentioned, wind coming different intensity in every direction. So region A1 carry between point and blow hardest from the west, as you can see. So we need extra resistance from the west side. So that's the intensity. So sometimes when you look at the structures, you might see some of the strong beams, and if it is sitting on some of this wind intensive region, you might see that some of the structures might have a what we call the bracings and strong beams and columns sitting on the west side. That means that your wind is blowing strongest from the wind side. So that's the physical meaning from these tables. This MD, let me write the name of this MD. The MD is wind direction multiplier, and that is given in the clause 3.3. Now, wind direction multipliers, let me draw it up because it has 8 different values. So you have north, you have 8 different values. Okay, let's read them with me. So what was the region again? Region A3, I believe. North is 0.85 MD value, right? So 0.85, and that is north. That's good. Let's read 2 at a time. 0.8 for northeast and east. So you have 0.8, that is northeast, and east it has 0.8. Right. Let me go back. And then you have southeast 0.8 and south 0.8. Again, sorry, 0.8 southeast and 0.8 south. And let me put all these arrows here so you can go, and let me put all these details here. This is west, and this is northwest, this is southwest. Okay, so we just need to read from the tables. Now we are here, southwest 0.85, southwest 0.85, west so west is 0.9 and northwest 1. 0.9 and 1. Right, so this is a MD. It has 8 different values, okay, depending on the cardinal directions. There are 8 cardinal directions. So in the Canberra, where does the wind blow hardest? By looking at these diagrams, can you tell me that if you are designing the building in Canberra, which side is the hardest wind blowing according to the standard? That you can see one is sitting there. So in the Canberra, you might have a hardest wind blowing from northwest. Okay. So MD is done. Any questions so far? By the way, we have half an hour finished. So I hope it's not fast. Look, when you do the opening of the door, closing of the door, this case might change. Okay, this is just I would just want to have a feeling at the start of these examples. This case might change. when you combine the two cases, external and internal pressures, and you keep this door open, this door closed, and I will show you how to combine those cases. So this scenario might change, but at the moment I'm just try to have not blindly follow start. I just want to have a physical meaning when you flow through the example. It's just not just copy from the standards and putting those details. So that's the one, but it's not saying that okay, our primary designs are just now started here and we will just going to do northwest. No, there is more details coming along. Okay.
Sure.
All right. Thank you.
Thank you.
Thank you, Heather, and thank you for those questions. So hopefully it gives us me the time to breathe as well. Otherwise, I keep talking. All right. So next one, we are going to go back here, our magical page. That magical page will tell us everything that we done VR, we done empty. Now these are three. They put it in the bracket. We call site exposure multiplier, and the first site exposure multiplier called terrain height multiplier, and that is given in section number 4. So let's go there. Let's go there. Section number 4, site exposure multiplier. We have terrain categories, and then you have these terrain MZ terrain height multipliers. So if you turn the page over, you need to have a table 4.1, but before using the table 4.1 for MZCAT, we need to decide which terrain categories we like to go for. Now let's say we go back to this table here, sorry, this page here. So this page here, we have terrain category 1, plain rivers, canals, lakes, and exposed bay, wind direction. So I have put some notes here. Airfield, low resistance to wind blowing. So particularly if you have terrain category 1, it generally don't have much resistance of your wind blowing. Terrain category 1.5, open waters, when the wind blows is enough waves that cause the resistance to the wind. So some extra resistance due to the wind blowing. Open terrain with obstacle, farmland and clear subdivision. So I think that is very useful, that if you have a farm land or subdivision, isolated tree and uncut grass, you have terrain category 2. You have terrain category 2.5. For those details between 2 and 3, you can take it 2.5. Terrain category 3, probably suburban housing. If you are designing your house in suburb, you will have light industrial estate or dense forest. So you will go for terrain category number 3. And terrain category number 4 is well developed industrial complex. In a city, large building all around the place of provide the resistance to the wind that slows the wind down. Okay, so I put those notes. Probably the common one that we use is the terrain category 2. That is the most common that falls in the terrain categories 2. So we just take I think that is called MZCAT. Let me write it down, MZCAT, and that is called terrain height multiplier, right? And if you need more information, you can get it from the clause 4.2. So first of all, we need to decide which terrain category we are designing for. Terrain category number 2, and say that TC2, and that is from clause 4.2.1. Right, so we have terrain category 2. So once you decide the terrain category 2, you come back here. And terrain category 2, table 4.1. We are here in terrain category number 2. By the way, yesterday I forgot to tell you that, look, where was the one? Somewhere here. You cannot see one in anywhere in the tables. Only the one is given here. Terrain category number 2 at 10 meters. What does it mean? That this is the reference value. With this reference, all other values are are calculated. So this is the one is the reference value, that terrain category number 2. So they have done the terrain category number 2. They put that 10 meters height and they put this MZCAT as a 1. This is a reference. This is a reference for all others, right? So that's what the meaning of this one here. You cannot find one anywhere else. So that's just extra informations. For your calculation, those informations is not required. But I think every tables I just want to have some kind of feelings that's every tables tell you the story. So I just want to highlight that here. Now in here we need to just find this height Z, which is the average height. So if you go back to few page back, and there is a notes here that's these figures is helpful. You have a Z, we call them reference height, and this hedge is called average roof height, right? So if you are designing, let's say 20-story building, and your windward wall is going to be different at every story, so you have allowed to calculate that different reference height. Okay, in large structures, calculate windward wall load every floor Z individually. For 1 or 2 story structure, you might take the Z equal to H. So for our case, we will have Z equal to H. For our course, in our subjects, we will always have Z equal to H, because we will have just work with these 1 story or 2 story buildings. So you don't need to go for those cases. But for your informations, for your careers, this is the physical meaning of that Z. So over here we have Z equal to H, and H is basically sitting in the midway through your this slant roof that you have it here. So we just need to calculate this H from these figures. Go on here. So let me draw up that little triangles. Okay, so let me draw up these little triangles here, and in here, if you go back to the questions, it says that 5 meters, this one is 16 meters, and this angle is given 7.5. Right, so you have 3 numbers that you need to put. So first number is 16 meters, second number is 5 meters, third number is angle 7.5 degree. Now our question is to find this H, right? That is given in the figure number 2.1. Figure 2.1, that is explaining this height. Now if I draw this triangle here, which is right angle triangles, which I redraw here, let's say this is 7.5. Let's say I want to find this little height here, X. Okay, and this is 8, by the way, now 8 meters, because you have another 8 meters here, 8 meters. So if I do this, tan 7.5 degree equal to opposite over adjacent, so X is equal to 8 times tan 7.5. So I can say that 8 times tan 7.5, you get 1.05 meters. So this height from here to here is 1.05, but we need the halfway through, right? So the H would be 5 meters, this one, plus this halfway through 1.05 over 2 meters. So you have 5 plus 1.05 over 2. So you have 5.53 meters. Let's take a 1 decimal place, 5.5 meters. Right? So for that 5.5 meters, I think now we have all the details. Go back to this one here on table number 4.1. Let me zoom a bit so you can see it. 5.5 is sitting between 5 and 10. Unfortunately, 5.5 is not given. We have terrain category number 2. So we can do the interpolation. I will show you how to do the interpolation. So 5, 0.91, 10, 1. Okay, so you remember that one? 5, we have 0.91. And we have 10 meter height. We have 1, right? Now we need to calculate for 5.5 meters. How much mz cat? Basically, this is your height. This is your mz cat. Right? So let's say this is, we need to find mz cat. So we take a ratio, interpolation 10 minus 5. Okay, just watch me. 10 minus 5, respectively 1 minus 0.91. Right? I hope you understand. 10 minus 5, then you take 1, take away 0.91, equal to, similarly we take 5.5, take away 5, 5.5 take away 5, then respectively mz cat take away 0.91, mz cat take away point. Let's wait to activate this. .91. So let's throw some numbers there. Mz cat minus 0.91, 5.5 take away 5 over 10 minus 5 times by 1 take away 0.91. Right, so let's use the calculator. 5.5 take away 5 times by 1 take away 0.91 divided by 10 take away 5. You get 0. Sorry, what, something has happened. Not right. Let me redo it again. 5.5 take away 5. So let me 10 take away 5 divided by 1 take away 0.91, and then 5.5 take away 5, 5.5 take away 5 divided by 0.0092. Oh, yep, 0. That is okay. 9 times 10 raised to minus 3, and then you have mz cat minus 0.91. So you can calculate mz cat is equal to 9 times 10 raised to minus 3 plus 0.91. So 0.91, you get 0.92. So is the height is 5.5, category 2. That is the 0.92. So I think you just need to go physically check, make sure that you don't fall outside of this one. 0.92 is makes sense, right? It makes sense here that that if you get 0.85, it's wrong, because it should be fall between 0.91 and 1, because this interpolation, so linear interpolation. So you have 0.92 and mz cat. I think the next one that we need to find is the shielding multiplier and topographic multiplier, MS. So MS is called, I will show you where it is. Go back to the page where we have this MS. MS is again shielding multiplier, section 4. So if you go to the section 4 and you have this shielding multiplier, you have this shielding multiplier here. I think I have a notes here as well. So you are not allowed to take the tree as a shielding. Okay, so if you have tree, don't take it as a shielding, because people come with the chainsaw and they chopping down the tree. So shielding has to be permanent structures. Confidence it is, therefore life of the structures, buildings provide the shieldings. Okay, so yesterday we had some discussion about, you also need to take into account some future developments around your region. So I think there is some kind of survey need to be required, and some question need to be asked for this design. But in our case, We don't have any shielding, so we have ms equal to 1 because there is nothing we take into account. So close 4.3, it's talking about the shielding if you have any shieldings. So ms equal to 1, shielding multiplier. mt, what is mt? Last one. MT is called topographic multiplier, and it's again section. If you turn the one page over, you have these topographic multipliers. Now this topographic multiplier generally applied when your structure sitting on the hill, but we are on the flat ground, so our topographic multiplier is 1, is on the close 4.4, right? So for our case, let me rewrite, because we calculate everything. Let's rewrite site wind speed, and that is denoted by V site beta. And if I have a V site beta, I would say that VR, MD, MZ cat, MS, and MT. VR, how much was that? We calculated 45 meter per seconds. So let's put 45 meter per seconds. MD, it has the 8 different values. If you remember that I put at the start 8 different values. Okay, now we have a MZ cat, we just get it interpolation 0.92. MS is 1 and MT is 1. And if you use your calculators, which is basically 45 times 0.92, 45 times 0.92, you get 41.4 MD meter per second, right? So we still need to work out MD, because we have 8 different values of MD. So now you have this MD. We have done this MD. You can see here MD values here 0.85, 0.8. So now I need to multiply, because we have V site beta equal to 41.4 MD. So we need to substitute this MD equal to 0.85 to get the site wind speed from the knot, right? Because we multiply 0.85, you get knot. Probably I can get these pictures down there, so it will helpful to understand. Let me get these pictures down. Oops, knot is cutting, so that's okay. We snip it again. Let's snip this whole chunk. Okay, copy. Let's get it down there, so we have it in front of our eyes. Okay, so that's fine. Okay, so that's good. We have it in front of our eyes. So in here, let me reduce the size a bit so we can have another figures here. So here, I will read out this one, that we have these 8 cardinal directions, and for these 8 cardinal directions, we have MD equal to 0.85. So in here, we will have 41.4 times 0.85. 4 times 0.85, you get 35.2 meter per second, right? And that is your knot. I hope you okay with this one. Put this arrow. We have 0.8, so 41.4 times 0.8. 0.8. You get 33.1 meter per second, and that is northeast. 0.8, lucky, same one. So you have 33.1 meter per second, and that is east. 0.8 same, 33.1 meter per second, and that is southeast. You have 33.1 meter per second, and you have south. 0.85, I think we done 0.85 somewhere here, 35.2, because north and southwest is same, and that is southwest. And then 0.9, I think we don't need no 0.9, so 41.4 times by 0.9, you get 37.3 meter per second, and you have west. And then you have this one, which is 1, so 1 is easy, 41.4 meter per second, and that is northwest, right? Any questions so far? So look, we have 1 hour, but this look this, I'm not going to warn you, but I need a full attention. Okay, here this is a little bit tricky. Once you get it, it would be so far it's okay, but the one that I'm going to show you is it would be really challenging. I try to slow down and try to explain you in a way that you will get a full exposure. So what we have done so far, this is side wind speed. So far, step number 1, we calculated side wind speed, right? V side beta. If someone say that what is V side north, you say it is 35.2. If someone say that what is side wind speed on south, you say 33.1. So there are 8 different side wind speed, right? I hope you understand that. You have 8 different side wind speed given to you. Calculated. Okay, so this is step number 1. I hope there is not much so complicated. Now I want you to have it. Now we are going to calculate a design wind speed. Design with, this is the name of the next parameters that we're going to calculate, which is design wind speed, and that is denoted by V design and theta. Theta I will explain you in a minute. So this V design theta that we're going to calculate. Where are you going to find more information about it? If you go on clause 2.3, you have design wind speed. The building orthogonal design wind speed V design theta shall be taken as a maximum cardinal direction side wind speed V side beta linearly interpolate between the cardinal points within the sector plus or minus 45 to the orthogonal directions being considered. So complicated. It's not that, it's not easy that 3 lines they're written and how we going to mathematically do these 3 lines. But keep in mind these informations are here plus and minus 45 degree and so on. Another important informations that we have to making sure that whatever we calculate, it never gonna be less than 30 meter per second. So we're gonna make that check as well. As I mentioned, some smart structural engineers may come back and say that, oh, I know I follow the standards and I said I have a wind speed of 20 meter per second and I will design tiny steel beams or tiny frames because I want to save money. And if something happens, don't blame me, blame standards. So the standards play smart back saying that, okay, you play smart, I play smart, you always take 30 meter per second regardless of your design. Said, okay, whatever you do play, and then if you come across with less than 30 megapascals, we don't accept it. We write one line here that you need to take 30 meter per second at least as a design wind speed. We will check if there is any design wind speed. So they ask you to go in figure 2.2 and 2.3. So where is it? Here. So this is the one that we're going to use it full here. Okay, let me goes down. So let me take you through here. What is this? So this is your relationship of wind direction and building orthogonal axis. So you have a building, right? This is the building. I will take you through slowly. This is the building, and building has its orthogonal axis, like one passing from parallel to this edge and another one is parallel to this one. So they have 4, which is the building orthogonal axis. So this is building orthogonal axis, right? Now standard says that this axis that you are taking, take this orthogonal axis theta equal to 0. Take this one always theta equal to 0 as your reference one. So if you have tilted like this anyway, you can, if it is like this, you still take theta equal to 0. So I hope it is makes sense. Theta equal to 90, you take it along this one. Theta equal to sorry, I have written something. So they did not write much here, but you can say theta equal to 180 and theta equal to 270 here. So I hope it is clear. Theta, which is written here, right? You remember that theta. What is theta? Theta is building orthogonal axis angles. Okay, and how you going to measure that theta equal to 0 is just a reference that horizontal line perpendicular to this edge. So that is theta 0, 90 and on it. Now it has also given you the beta. You remember what is beta? Beta is your cardinal directions. So when you have north, your beta is 0. And when you have northeast, your beta equal to 45. Your east cardinal direction, they mathematically represented beta equal to 90. Southeast, they mathematically represented 90 plus 45, 135. And then south side, u plus 45 across, south side beta equal to 180 and so on. So I hope you understand these figures. So if you have building here orientations, you will have so in case if your building is oriented exactly on the north, then your theta 0 and beta equal to 90 sitting on the same side. So I hope you understand that. If your building is exactly oriented along the north directions, let's say this one, then you tilt this one, then theta equal to 0 and beta equal to 90 are on the same axis. So orthogonal directions of the building and cardinal directions will be aligned. That would be life easy, but here the life is complicated. So this is cardinal direction. I explained that. Beta. So look, this one is they have it at the 70 degree. I believe there is a 70 degree from here to here. It looks like a 70. Okay, don't worry about this. So side wind speed has 8 cardinal directions. Design wind speeds at 4 building orientations at front. Oh, okay. Another one, that front one is 0. So this is front, this is right, 90, back, and the left. Probably it will not make sense, but I think this is not, I'm not sure, somewhere I have written, but it will not be so much useful. But if you want to change it, that standard does not say anything about this one, but I think you keep this theta equal to 0 the way it is represented here. Some calculations are easier if the front is taken as as I mentioned, sometimes the calculation heap roof perpendicular along the side of the building, gable roof perpendicular to ridge, cardinal direction of the front. Okay, so this is all good. So I hope you understand this, both ultimate and serviceability. Okay, so that's all good. Now this is very tricky one. Okay, not tricky, but I will explain you this one in a definite manner. So, okay, let's crack this one. We have more minutes. Okay, all right, stay with me. Okay, I'm going to, I encourage you to draw this one by ruler. Okay, it is good to draw by rulers. Okay, so you draw this axis here. Again, you no need to remember, I copied from here. I draw this line and I draw these lines. Okay, so on x-axis I will put the cardinal directions, and on y-axis I'm going to put a side wind speed. Okay, that's I copied here. So let me copy that one. So here I will put cardinal direction beta, and here I'm going to put, oops, sorry, I'm going to put v side beta, meter per second side wind speed. Okay, and that is given in the figure number 3. Let me write that figure as well, figure 2.3 in the standard. Now let's start meaning let me show you. You have north 0, north 0. So let's put that one 0 north. Then second one, 45° northeast. 45° northeast. 90° east. 90° east. Then you have southeast. You need to add 45° here and southeast. Standard does not tell you, but it's you can figure it out yourself. Okay, southeast they just continue here, so we can do it from these figures, I believe. Southeast and then south, southwest, west and northwest and continue. And we add 45° every time we do it. And here 135 plus 40, 180 degrees, and that is east. And then you will have add 45 again, so 225, and we will have east southwest, and then you have 270°, and we have west, and then northwest. You just add 45 every time you put it, 315, and then northwest. I encourage you to use the ruler, and you can just mark it every 1 centimeter or 2 centimeters depending on the width of the page, and then you use the rulers. That would be the most effective way. Northwest, and then you have finally you have again north. Oh, sorry, this is 360°, and again north here. So that's full circle finish. Now I can stop. If you tell me that how did you draw this line, how did you put these numbers, or where did you get these numbers, or how you're telling anything. No questions, I take it as a no questions. Now I come back here. Now let me draw the orthogonal axis for our buildings, right? I can show you what I'm drawing right now. In this one, I'm drawing this line. So on the standards, you can see orthogonal direction of this one, which is theta equal to 0. I'm going to draw theta equal to 90, and I'm going to draw this one, and I'm going to draw this one. How it gonna help me? You go back to this orientation. Student ask me these questions. What we're going to do it orientation? That answer is coming here now. That you can see that your building is oriented 15° to here. So I am going to draw these two blue line. That is my theta equal to 0. That is my theta equal to 90°. Theta equal to 180. And theta equal to 270. Right. So I'm going to draw these 4 lines. And if I want to have this 15°, and if I just draw this line like your sorry, this is should be horizontal. If I draw exactly the horizontal and vertical, if this one 15, you agree with me, this is 15 as well. This is 15 as well, and this one 15 as well. Do you agree with me, right? So these lines that you are drawing like north, east, south, and west. If I draw these 4 cardinal directions, you have given this one given to you, 15 degrees given to you. So with all north with north on the left side you have 15. So you have 15 on this side, on 15 probably 15 going on this side, and 15 are going 15 are going on this side, and this side. So you can see these full circles are going this way. Now let me put these details here on my diagrams. So which diagrams I'm talking about, I'm going to put it here. Please pay attention here. So let me use different colors. So I have this line going here, blue one, and then I'm drawing this one. This blue line, which one I draw? This one and this one. I can repeat again. I draw this one and I draw this one. I'm going to label same, theta equal to 0, theta equal to 90 plus 90 plus 90. That's what I'm going to label it now. So let me label that theta equal to 0 degree, theta equal to 90 degree, theta equal to 180 degree, and theta equal to 270 degree. I hope it is makes sense. So in the figure it says that in the question you have 15 degree going this way. So 15 degree from here, 15 degree from here, 15 degree from here. Any questions so far? I can stop and you can ask me the questions if you have any. I think there is no questions. I hope it is not fast and I hope you understand what is going on. Now, how am I going to explain? Okay, let me explain this theory as well with the 45 degree and so on. So let's say you have, let me draw these 8 directions. So this is north, south, east, west, northwest, southeast, southwest, northwest. Now that is our cardinal directions. Now we have, let's say this blue color one, let me draw this blue color one, that orthogonal directions. So if I show it to you here on the standards, I have drawn these first 8 different directions. Now I'm going to draw this blue one here. Okay, so this blue one that we're going to draw is this, going to draw this one, right? I hope you understand that. Now the standard saying this one, that you need to take plus or minus 45 degree from the theta. Okay, so that's good. So you take, so look, this is 15. You remember this one is 15 degree. Now from this one, let me draw the green one. So if I draw so let me draw up the line here, which is plus 45. Let's take it, let's say this is negative 45 if you like, negative 45, and I will going to take another plus 45. Where is measuring? From this line. I hope it is makes sense. I think it's a little bit complicated, but I will tell you how it's working. This is the one that's telling me to do that. From your theta, you take plus and minus 45. So from this theta, which is theta equal to 0, I take 45 minus and I take 45 plus. Now standard saying that whatever the velocity falls in this sector, also this theta, if I want to calculate what is the velocity going in here in theta equal to 0, what you're going to do it, you take the maximum of all the values. You need to calculate this one as well. You have these values, you have these values, you have these values, you have this 1, 2, 3, probably 4, 5, 6, 7. You have 7 different velocity, and you take maximum out of these sectors will be the velocity going along this one. You understand that? So I can repeat. So it's saying that, look, it's saying that, okay, this is your theta. You take a 45 plus and minus from that theta, and all the wind coming from this region, whatever falls in this region, you have this one, you have here, you have here, you have here, you have here, whatever you coming, you take maximum, and that's the design wind speed theta equal to 0. Similarly, you come back here, you take a 45 plus and minus from this theta, whatever falls in that one, you take the maximum. You have this one, so you have end up with the 4 direction wind speed only. So you have this one, you take plus and minus 45 degree, you take maximum value that falls in that sector. And then for this one, you have this 45 degree plus and minus. From this line, you make a sector of plus and minus 45 degree. Any wind coming from that sector, you take it maximum. Does it make sense physically? I can stop here. And oh, sorry, I keep it the figures so you can ask the questions. But does it make sense? Or I can put the standard. So that's the meaning of these 3 lines here, plus and minus 30, plus and minus 45 degree, and so on. So we end up with taking 4 design wind speed, but taking maximum in that regions, right? All right, so I take it no that you understand that concept. Now how we do it, this is looks complex here, so how we do it on this one. So these figures will going to help, that is also given in the standard. So let me put the values there. So for the north, help me out, for the north, what is the velocity? Site velocity, site wind speed. It's 35.2. Everyone agree that here you need to approximately take a some scale 35.2, and that's unit is written here meter per second, so I'm not writing it. Everyone okay? Because it's written note here, so I put 35.2 meter per second. I stop here, you tell me if you don't understand. Let me drink water and then we start. Any questions? 35.2. Everyone understand, I believe. No questions. 35.2. Then we come in northeast, 33.1. Northeast, and we just going to put little bit down. As I mentioned, there is 33.1. And do you want me to write 33.1? Probably it will be messy. But anyway, we're going to write, let's say write it down here. 33 point, how much was that? 33.1. So it is 33.1 meter per second. By the way, this point is for here, okay? That's I written because it might get messy, but let's see. Then east is 33.1 again. So we go horizontal line, 33.1, and that is 33.1 as well. We're gonna put it as up there, but I don't want to create a lot of traffics there, conjunctions. Make it nice and clear. So southeast 33.1. So draw horizontal line, southeast, and then you have 33.1 meter per second. East, sorry, what happened here? Oh, sorry, this one would be south, I believe. This one would be south. So south is done, and then south 33.1. So let's draw the horizontal line. 33.1. Southwest 35.2. So we go back all the level here that it's here. So we need to go back to the same levels, and that is here. Let me erase this. So I'll just go back. I'll just draw by scale so if we can physically see. So that is 35.2 again. Then southwest, then after we have west 37.3, which is you know the west one, right? The west one are the worst one. So you go up, you can see this speed velocity speed is going up, and that is how much was that? 37.3. 37.3, and then you go back and do 41.4. So you have again you're going to go up. Oh, sorry, let's put the green line, and that would be your 41.4, and then again north is 35.2. So if I just take it on the same line of here, somewhere here, and then you draw back to 35.2. Any questions? How I draw this green and red dot and how I put the numbers? Okay, here you put 35.2 again. So here 35.2. Let's put for the completeness 35.2. Basically these dots are these numbers are next to the dots. Okay, I just put down here to just give these lines nice and clear view. Any questions there? You may ask me if you said, okay, how did you put this red dot for east or south, or I did not understand this number, where this number is coming from, and so on. You can tell me. All good. I think I take it no, there is no questions. Now, this one is a little bit tricky. Let me give it to go. Now let's start with this theta equal to 0. You can see this blue line, right? Theta equal to 0. Please pay attention, and I will show you on the standard as well. Let's put this water bottle away. So I'm just talking about here. We like to give it to go how much velocity is coming theta equal to 0 for this sector plus and minus 45 degree going this sector. So let's work on theta equal to 0. Everyone happy? Theta equal to 0, that's our starting point. Now theta equal to 0 makes, look at this arrow going this anti-clockwise towards the, so the theta equal to 0 is falls between east and northeast. Everyone agree? The blue line is sitting between east and northwest, measuring 15 degree from the east. I repeat again. Theta equal to 0 line, that theta equal to 0 line, which is blue line, dotted line, is sitting between east and northeast with 15 degree from the east. Okay. If you want to write it down, write it down. So I want to draw the blue line here on this chart. So blue line for theta equal to 0. Give me a minute. My computer is just, I need to put the passwords. Give me a minute, okay, please. Okay, that's fine. My computer is back. So between east and northeast, and we have this dot line 15. So east, northeast, and we have question me how on earth you draw this one if you don't understand. I can repeat again. Theta equal to 0, blue dotted line sitting between east and northeast. Theta equal to 0 line sitting between east and northeast, measuring 15 degree from east. towards northeast. You can stop me. How did you draw 15° or theta equal to 0 from the east if you don't understand? Give or take a time. I draw from this figure that theta equal to 0 line sitting between north and northeast with the 15° from the east towards northeast. So 15° towards northeast. Everyone okay? It seems that everyone okay. Now, this business comes next, that this green line, that 15° going to the left and 15° going to the right. Now this 15° going to pass northwest and it will sit somewhere here, because if you take a 15°, because this is 15, so that would be 30, that would be 15, right? So you can see this line, the green line which I am going to draw now, this green line, let me put it out. This green line I'm going to draw, that green line is sitting between north and northwest, that measuring 45° from this line and is measure 15° from northwest. So green line that passing from what happened here? Okay, southeast, northeast. Okay, so we will have this green line that we're going to draw, because if you have this one is 30°. Do you agree with me? Because this is 45. From here to here, the distance from one this between this one is 14. So if it is 13, I have, if it is 15, I have another 30 here. And I want to draw this green line that will going to give me this extra 15°. So it makes 45° from the theta equal to 0. So that is telling me this one, that you have 45° from your theta equal to 0 on the one side. So that is 45°. On the other side you have 15, and if I add another 30, then I will get 15. So let me draw that another line which is 30. So that is 45°. That is 45°. You with me? So that's 45° on the left side, 45° on the right side. That's how this plus and minus works. Do you agree? You can stop me and ask me questions if you don't understand that. So in this region meaning between these two poles, we need to pick the maximum velocity. The maximum velocity is sitting here. Do you agree? Between these two poles, that two green poles, which is 45° plus, 45° minus, we need in this region that maximum value would be the velocity at theta equal to 0. So I need to do the interpolation here because I don't know this value, right? Because look at this one. This one here, I don't know. I know this 35.2 here and 33.1 here, but I need to calculate these values, right? So we need to do the interpolation. Stay with me. So when you have theta equal is when you have 0, you have 35.2. Let me write it down. When you have a 0 beta value, you have side wind speed of 35 point how much? 2. You understand that, right? I just copy that 35.2 meter per second. So when I have 0, I have velocity 35.2. When I have 45°, I have velocity of 33.1. So when I have 45, I have velocity 33.1 meter per second. Understand that? You can stop me if you don't understand that one. So I just copy that one. Now I need to find the velocity at 15 degree. Do you understand? Because if you measure from here to here 15, from here to here 30, so total 40, because you have already this one 15, so you have 30 and you have this 50. So my intention is to get this 15 degree from these points, or you can calculate 30 degree from here as well. They will be both same. So I want to know when I have 15 degree from here, what would be my velocity? So if I have 15 degree, I think I can write 30, I believe. So if you have a 15 here, then I have 30 here. Let me see if it comes true or not. So let's write 30 here, and then you can find this velocity. How they done it? Let me check. 45 take away 30. Yeah, probably. Okay, so let's take a interpolation now. So 45 take away 0 over 33.1 take away 35.2 is equal to this 30 take away 0 over, let's put this x here that we need to find, x take away 35.2. So let's say x minus 35.2 equal to 30 minus 0 is 30. This 45 comes here times by 33.1 take away 35.2. So we have 30 times 33.1 take away 35.2 divide by 45, you get minus 1.4 plus 35.2, you get 33.8. Is it right? Yep, 33.8, that's correct. 33.8 meter per second. So I would say that in this theta equal to 0, I would have, this is here 33.8 meter per second. So theta equal to 0, which is here, in this one you will have, let me draw the neat figures here, and this blue line is here, and let me draw this one. So theta, we design theta equal to 0, you have 33.1, is it 33.1 or 33.8 meter per second, and is greater than 30, check it, greater than 30, so it's okay. Everyone okay? We just take it maximum value from 45 degree plus and 45 degree minus. All right, so that's one theta equal to 0 done. Let's go for the next one, that theta equal to 90. Again we take 45 degree on the both side. So let's do it. So I need to draw the line again, this blue line which I'm drawing it here. Do we have blue line here as well? Oh yes, here is more nice, clear. So you have blue line sitting between south and southeast, measuring south 15 degree. So between south and southeast, between south and southeast, theta equal to 90 degree and measuring 15 degree from south, right? Okay, so blue line is between south and southeast, measuring 15 degree from the south. And then again we put 45 degree on left side, so this is 45 degree on the left side, and then another 45 degree would be here, because this is 15, this is another 30, right? So I would say that I draw another pole here, and this is the pole here. So this is the region now that we're going to work through. And by the way, this one is 15, so this one is 30, right? And that is remaining one. So we need to calculate this red one here, because that is the maximum velocity that we get. So here we're going to do this between the interpolation between this 180 and this 225, and it's gonna measure 30 degree from 180, so we can calculate that. So let's do that. 180 33.1. 180 beta 33.1. From this 180 you have 210. So when I have 210, we need to calculate. Let's put x. And then another one you get 225, you have 35.2. 225, 35.2. So do the interpolation. 225 take away 180 over 35.2 take away 33.1 is equal to 210 take away 180 over x take away 33.1. X take away 33.1, 210 take away 180 times by 35.2 take away 33.1 over 225 take away 180. So let's use the calculator. 1.4, and then you have x is equal to 1.4 plus 33.1. You get 34.5. So you have this one is 34.5 meter per second. So theta equal to 90, I would say that maximum value is 34.5. So here we design theta equal to 90, which is 34.5 meter per second, which is greater than 30. So that is okay. I hope you understand what we are doing. Go the next one. That line is this one, 180. 180 is sitting between southwest and west, measuring 15 degree from west. Okay. So theta equal to 180. Theta equal to 180. Measuring, sorry, what? Measuring from the west. So theta equal to 180 between west and southwest, measuring 15 degree from the west towards the southwest, right? Yes, towards the southwest arrow is telling me. So still fine. We go, this one is 15, I believe, 15. So this point is still valid. So this 34.5, we're gonna take it, and we have to. So this one, this point, this pole is still going to be our leaf pole. On the right side, you have 50 and another one 30. So you have, this is 30, this is 15. Right, so we this is the points, target point now, because between this one you have these maximum points, right, for theta equal to 180. Now let's do the calculation again. 270, 37.3. 270, 37.3. Then you have 270 plus 30. So you have 300. We need to calculate, and then this big one, which is 41.4 at 315. 315, 41.4. So quick, 350 take away 270 over 41.4 take away 37.3. 300 take away 270 over x take away 37.3. X take away 37.3. 300 take away 270 times by 41.4 take away 37.3 over 315 take away 270. So 300 take away 270 times by 41.4 take away 37.3 divide by 315 take away 270. So you have 2.73. Let's get the 1 decimal place. So x equal to 2.7 plus 37.3 plus 37.3, you get 40 meter per second. So in here we have here 40 meter per second. Now that 40 meter per seconds that we have, we can take it theta equal to, we design theta equal to 180 40 meter per second, which is greater than 35, we greater than 30 meter per second. So it is good. Now the last one, that theta equal to 270, drawn between north and northwest, measuring from north. Drawn between north and northwest, measuring from north, and that theta equal to 270, and that measuring 15 degree from the north. And let me continue this one, north and then northeast as well. We need to just this one again, put this one for completeness, northeast, and that northeast has a 33.1. So let's continue that line. So you have this 33.1. So let's draw the 45 one. Again, this is 15, this is 15, and we have 30. So this is 30 here, and we have another 50. So this pole still going to go in here, which is 45 degree, and you have 30 degree pole here. So that is measuring 45 here and measuring 45 here. So in between, I think nice view here. That is your maximum peak, and that maximum peak is 41.4. So it's easy now because we no need to do it. We design theta equal to 270. You have 41.4 meter per second. Right. So this is the final one, that you have 4 different design wind speed. Okay. I can write it nicely somewhere. Okay, let me write it down here. So you have theta equal to 0 degree, theta equal to 90 degree, theta equal to 180 degree, theta equal to 270 degree. For here we got 33.8, 34.5, 33.8, 34.5. I remember this one just now, 41.4, and the last one we got is the 40 meter per second. 40 meter per second. So this is all we design theta. There are 4 speeds given here. All are greater than 13 meter per second. This check is okay. All right, question time. So these are the speed hitting. So these are the speed hitting. I can show you 33.8. So this is the directions. You have speed coming on this wall 33.8. I think here 34.5. Here I don't remember that, or this is 41.4 meter per second. That's what we found, right? This is meter per second. And then the last one that we got is 40. Yep, that is 40. That's what we found, right? You can think of this is structures. We found the perpendicular wind coming onto that wall by taking 45-degree left, 45-degree right. In that zone, you have this this different velocity that's coming. Questions? If you have